just an aluminum reducing agent. And our polar protic solvent with acid workup, remember that whenever we have an organometallic species, so if it is copper, lithium, aluminum, or magnesium in our Grignard, we want to make sure that the second step always provides some source of protons. Those always need to be paired together. And in this reaction, our final product will generate an aldehyde on one side of our molecule and an amine on the other. So let's just make sure I haven't lost any carbons. I'm going to number them. So let's call it atom 1, 2, 3, 4, and 5. And I have atom 1, 2, 3, 4, 5. And there should be a methyl on carbon 4. I did lose an atom. There should be a methyl right there. All right, so that would be my final product. And now what we want to do is we want to go through the mechanism. So let's start off with our starting product, or our starting reagent. So we have nitrogen that has a methyl, and this should be a carbonyl. And we'll just write diabol as some hydridic species that contains aluminum. So I'll write it as HAlR2. And then our hydridic species will attack the carbon in our carbonyl and push electrons to oxygen, which allows us to generate our tetrahedral intermediate where we've added a hydrogen. Now our oxygen has a negative formal charge, right? There's still a methyl on our ring and a nitrogen that has a methyl on our ring. And then in the presence of AlR2+, we can form a new bond here, and this generates a more stable species, right? So in our more stable species, we still have nitrogen, our ring. We've added a hydrogen, and now we have OAlR2. And our next step is to use the lone pair of electrons from nitrogen to generate a double bond. And this causes our OAR2 to be a good leaving group. So from there, we'll generate a double bond between nitrogen and carbon. And now this carbon also has a hydrogen attached, right? And then we have an alpha hydrogen that can be deprotonated by OAlR2-. And when we deprotonate that alpha hydrogen, because it's so acidic, we'll push electron density back to our positively charged nitrogen. So now we should have nitrogen with a lone pair, right? We now have a double bond in a different position of our molecule. And then we still have a hydrogen present here. Sorry, I didn't actually, did I change the location? Yeah, so now we have a double bond in a completely different position. And now what we want to do is in the presence of water, sorry, in the presence of acid, H2OH, we can use the pi electrons from our double bond to protonate our carbon, and then the lone pair from nitrogen can make a bond between carbon and nitrogen. And this allows us to regenerate our carbon-nitrogen double bond. Right? And now we still have a hydrogen here. We've technically added a hydrogen here now. We've technically added, sorry, I'm missing a step. Sorry. So we have a hydrogen here, and then with water, we've added a hydrogen here. And now we have another, with our acid, we've added a hydrogen here. With our equivalent of water that we just made, we can treat that as a reagent that can attack our carbon and push electrons to nitrogen, which has a positive formal charge. So we just want to get rid of that positive formal charge on nitrogen. So now nitrogen is now neutral again with a lone pair. We've added, so this has a hydrogen and it also has an OH water, right? And then now the next step in our mechanism is to deprotonate our water, and that's going to happen with a proton transfer. So we'll take a hydrogen from water and push electrons to oxygen, and this allows us to generate a hydrogen, a methyl, and then this should have a methyl, oh, sorry, a methyl there. We've added an OH to this part of our molecule, right? So now we have our ring structure, and now nitrogen should have a positive formal charge. And with this positive formal charge, we want to eliminate it again. So whenever we give nitrogen a positive formal charge, we want to eliminate it. And we can do that by regenerating our carbonyl. And then this carbon-nitrogen bond is broken. So we'll show that bond breaking there. And this allows us to open our ring. So when we open our ring, now we should have a protonated carboxylic acid, protonated aldehyde. And then we have the other carbons in our molecule. So let's number them so we don't lose track of them. This will be atom, I just want to make sure I don't lose it. This will be atom 1, 2, 3, 4, and then atom 5 will be nitrogen. And now nitrogen should have a methyl and 1 hydrogen with a lone pair, right? And now, in the presence of the water that we've generated, H2O, we can deprotonate our aldehyde and then remove the formal charge on our oxygen. So now we have our deprotonated aldehyde species on one side of the molecule. Now on the other side of the molecule, we should have generated an amine. So on one side, we have an aldehyde. On the other side, we have an amine. Right. Any questions about that? Yeah, so that one feels a little bit longer. And then obviously based on your professor, you'll be told whether it's a mechanism that you need to know for any exams. So make sure you just take a note of that. For the most part, it's a really common mechanism that you do need to know. And then for the last question, let's go through. So I'm going to erase this. And now we're going to go through the mechanism for one of the predicted products that we actually had. So we wanted to take an amide and generate an amine. And the way that we can do that is with a strong base in the presence of a halide as well as water. So the product for this reaction will be CH3, oh, that doesn't look like a 3, CH3, NH2, and nitrogen has a lone pair. So we've just generated our amine, and this, what really is occurring, right, is we can see that our NH2 and CH3 become attached to one another, and it's equivalent to just losing that carbonyl completely, right? So this is a really interesting reaction that allows us to completely eliminate our carbonyl functional group, including the carbon. So normally we've seen reactions where that internal carbon that we see here is retained, but we just lose the oxygen. But this allows us to lose both the carbon and the oxygen in our carbonyl. So let's go through the mechanism of how this happens, because it is a pretty interesting one, and you need to know it. Okay, so the first step is generating our amidate ion. And what does that look like? So for our amidate ion, we'll start with our amide, right, which has a nitrogen, a lone pair, and a hydrogen. And in the presence of our strong base, OH minus, we can deprotonate our nitrogen species and push electrons to nitrogen. So this is probably something new than you've seen before, because now we're giving nitrogen 2 lone pairs, a hydrogen, and a negative formal charge. So you can imagine that this amidate ion that we've just generated has a resonance form, possible, right? Where we can push electrons to form a double bond there, and then allow oxygen to carry those electrons as the more electronegative element. So now we have a double bond there, a hydrogen here, right? And nitrogen still has 1 lone pair. So we can imagine that resonance form being generated. And if we look at this resonance form, we can say that in the presence of Br, we can treat the pi bond in this resonance form as a nucleophile that can attack bromine and generate Br minus, which is the good leaving group. And as we do that, we're going to need it to form a new bond to our carbon that's attached to oxygen. So we'll push electron density back to that carbon, right? And then from there, we should get, what am I doing? I want to redraw those arrows. So from there, our next step will be to actually deprotonate our nitrogen once again. So we'll deprotonate our nitrogen. So now we have O. This nitrogen should still have a hydrogen and a lone pair. We've added Br. We have Br minus present. And then in the presence of another equivalent of base, we can once again deprotonate our nitrogen and regenerate our negatively charged species, right? So the second part is where we generate a carbonyl. I miss an arrow pushing. So a carbonyl nitrogen now has 2 lone pairs with bromine. And what we're saying now is with our push-pull mechanism, we'll have electron density in our ethyl being transferred to nitrogen. As we do that, we'll transfer electron densities to carbon, and then between nitrogen and carbon, and we'll lose Br as a leaving group. So when we have this reaction, this is our push-pull rearrangement, right? So this is our push-pull rearrangement. We're saying that the nitrogen is pulling the ethyl and the bromine is being pushed away, and this generates our isocyanide species. And this is how we can lose our carbonyl, because now we have a nitrogen with an ethyl, we have a carbon double bond O, and we have a carbon double bonded to nitrogen and a carbon also bonded to oxygen. And don't forget that we also still have Br minus floating around. And now what we can do is we can hydrate our isocyanate. So I'm actually going to go to a different page. So we'll take this molecule, our isocyanate, and lone pair ethyl, double bond C, double bond O. And we want to hydrate our isocyanate with water. And that just means that we're going to treat water as a nucleophile that attacks the carbon in our isocyanate and pushes electrons to nitrogen, right? So in this reaction, we'll generate a negative charge on nitrogen once again, because now it has 2 lone pairs. Carbon should have a carbon double bond. We have water being added, and oxygen now has a positive formal charge. And now what we want to do is use our negative electron density or extra electron density on nitrogen to deprotonate our water and generate an extra lone pair on oxygen. And then from there, we'll get our reaction where we have a nitrogen that now has a hydrogen, and an ethyl, it only has 1 lone pair. There's a bond to carbon, a bond to oxygen with hydrogen, and a lone pair, right? And then in this reaction, our nitrogen can deprotonate our alcohol OH group once again, and this generates a double bond between carbon and oxygen, and this causes us to lose our nitrogen as a leaving group. So this causes that bond breaking there. So we'll see bond breaking occur here based on the new double bond that we formed between carbon and oxygen here, right? So once we do that, now we've generated our final products, which is our carbon dioxide, and then we've also generated our desired amine. So those would be our 2 final products there. All right, cool. And then this 4th step right here is called decarboxylation. Okay, so that's our decarboxylation step. And the 3rd step that we saw here, sorry, this isn't decarboxylation, I put it in the wrong place. This step is where we hydrate our isocyanate, and then this last step here is decarboxylation. All right, cool, awesome. Any questions? No? All right. So actually, you may see a slightly different mechanism in your textbook or another kind of another textbook or some lectures. And the main difference is the 2nd step, where our push-pull rearrangement looks a little different. And for our push-pull rearrangement, what you may see instead is after we've generated our aminidate, the bromine species, right, that has a negative formal charge, you may actually see the loss of our leaving group first. And this would generate a nitrene. So our nitrogen with a lone pair, we have Br minus, with 2 lone pairs and Br minus. And this may be another way that you'll see the electrons being, or the methyl shift occurring, or the alkyl shift occurring, and then lone pairs from our nitrogen will get transferred there. And this is how we would generate an isocyanate species instead. So now we have our N with a lone pair, and now the methyl is there, right? We've now generated a double bond to carbon in the center. And then this also still has a double bond to oxygen. So this is another way that you may see this mechanism occur. Because by moving the methyl group, by having the alkyl shift, we've removed a bond from carbon, right? And because we've removed that bond from carbon, we're allowed to add a new bond to carbon from our nitrogen lone pair. So you can imagine that the bond that gets shifted, or the new bond to carbon, would be a carbon-nitrogen bond here. And our bond that gets shifted is